Welcome to this video. I am Quentin Bay, and I will present you our demonstration paper titled Indoor Ultra-Wideband Localization, LocURa4Iot Testbed and Dataset Presentation. This work was presented during the LCN 2022 conference. First, a few words on the LocURa4Iot Testbed. It is a platform devoted to the performance evaluation of ranging and synchronization protocols in wireless networks. There are currently 64 nodes in the testbed, fixed and mobile. The mobile node is on a rail controlled by a stepper motor, so the position of all the nodes are known during an experiment. These nodes are based on the DW1001 module from Corvo, which is equipped with ultra-wideband and BLE transceivers. It enables comparison between heterogeneous physical layers. Some of the nodes are even equipped with LoRa transceiver. Today's demo is focused on the ultra-wideband aspect of the testbed. The node can be used as bare metal platform by the researchers. They can be programmed with custom firmwares. The main deployment of the testbed is an area located in an office setting over the whole first floor of a building. It covers a 23 by 13 meter area, roughly 300 square meters. The testbed provides interactivity over the MQTT protocol. The node serial links are bridged over specific topics for each node, and the mobile elements are controlled in the same way. For example, here, we will receive the rail actual position in real time in the top left terminal and publish position command in the top right terminal. And we have in real time the position of the rail updated in the top left terminal. Several other MQTT agents are present to help the user access ranging error, position error, and so on. We have released the dataset in the context of this demonstration. This dataset has been generated on the LocURa4Iot testbed according to the following experimental setup. One mobile node, the node 183 here, performs distance measurement with a subset of the fixed node of the testbed. The mobile node is moving on the 7 metal rails here by 10 cm increments. At each step, the mobile node performs 10 distance measurements with the fixed node using the well-known TWR protocol. Quite simply, this protocol consists in the exchange of two messages. The mobile node sends a request to the fixed node, which reply, and using the timestamps of T1, 2, 3, and 4, we can compute the time of flight of the message, and from this, the distance between the two nodes. We have selected several fixed nodes to showcase different propagation conditions. First, the node 184, which is always in direct line of sight with the mobile. Then, the node 100 and 101, which are always in a non-line of sight condition, with a drywall between them and the mobile node. In the same way, we have the node 150, which is always in line of sight condition with the mobile node, but here the walls are thick, load-bearing brick walls. And finally, we have the node 180 and 171, which are either in direct line of sight of the mobile node or in non-line of sight condition, depending on the course of the node on the rail. Each ranging is recorded as a JSON dictionary, containing all the recorded value for this ranging. These include data pertaining to the TWR protocol, such as the timestamps here, to the radio transmission, such as the received signal strength, to the node position while this ranging was done here, and also it records the channel impulse response. So the channel impulse response, represented here on this graph, is a very information-rich record. So here we have this gray line represents the instant that was decided by the hardware as the arrival of the frame. Each nanosecond we have the hardware sampled the power received for that frame. And what's extremely interesting is that here we can see a first peak corresponding to the arrival of the first packet, and here a secondary peak which corresponds to the reflection of this packet on something, probably a wall, maybe the ceiling or the floor. It will be more clear with the video. So here in this small demo setup, we have two nodes. The node on the left sends 10 messages per second. The node on the right prints the channel impulse response associated to each of these messages. And here on this graph, we represent the last 10 channel impulse responses that were received. So we can see that, first of all, the channel impulse response is stable. When nothing in the radio environment moves, all the messages overlaps nicely. We'll start the demo. And here we have an operator who puts their hand between the two nodes. So first thing, it modifies the channel impulse response because there is an obstacle which attenuates the signal. When the obstacle is removed, we go back to the first shape. And now, what we can see here is a very interesting phenomenon. We can see that we have two paths. So the first one directly through the end of the operator, and a second one, which is likely a reflection on the white wall in the background. And what's extremely interesting here is that we see that there is more power received through the reflection than through the direct path. It means that there is an obstacle. This is extremely important to detect obstacles that could impair the accuracy of the distance measurement. And now I will show you some results from our datasets all generated in the testbed. So first, quite simply, ranging errors. So here we have the ranging error between the mobile node 183 and the node 101 as a function of the position of the mobile node on the rail. We can see two parts in this graph. So the first part here corresponds with a high average error and high standard deviation of the error. And the second part where these two values are smaller and stable. It matches quite nicely with the corner of this office, which blocks more signal compared to simply one drywall here. In the same way, we have here the ranging error for the node 150. And once again, we have two parts in this graph. First part, which corresponds to the position of the mobile node in the beginning of the rail. And second part, after the mobile node have cleared this corner here. Once again, we can see the impact of this obstacle. Some ranging were able to go through these walls, but only a few. And in the remainder of the course of the rail, it seems that the ranging error does not depend on the position of the node. What we can also do is to take a look at the channel impulse response in these loss and unloss setups. So first, we'll see to compare easily between line of sight and non-line of sight, we will use the node 180, which is also included in the dataset. So here we have our mobile node here, the green cross, and we have, as earlier, the last 10 channel impulse responses. What we can see here is that we are clearly in a non-line of sight situation. We have a first path with small received energy compared to secondary reflection here with a high received power. This reflection is likely reflection on this wall here at the bottom of the map. So let's run the experiment. We'll see that each time the node moves, while the node is moving, the channel impulse response is not constant. But once the node stops, we get nicely overlapping shapes. Here we are still in the non-line of sight part of the course of the node, and we still have this smaller first peak. But if we let the experiment run, once the node has cleared the obstacle, we are in a normal situation with the first path with the most of the power and secondary reflection with less power. So this is the difference between N-loss and loss channel impulse response. But what happens for our other nodes, which is always in non-line of sight situation? Let's start the experiment. So on the first part here, behind the obstacle, we will receive only a few messages because of the attenuation of these walls. So nothing much happens here. we have a few that go through. It looks like the shape of the channel impulse responses overlaps nicely, but we see that the received power is very low. Here we have the shape. We are still in the area that is masked by this corner. We have a shape that corresponds to an N-loss situation. A small first path, then secondary reflections with more power. And if we let the experiment run, we are still behind the obstacle, so we receive only a few messages. So that's why there is only a few updates. But once we have cleared the obstacle, we find again a coherent shape. And let's let it move a bit. And here, we have a very nice line of sight compatible shape with most power in the first path and some power received in secondary reflection. However, here we know for sure that we are in non-line of sight condition, because here this thick brick wall goes all the way through the building. So this is what we call a hard N-loss situation. There is no direct path, and it's difficult to detect. It would be extremely interesting to be able to tell that we are in such situation, for example, to increase the uncertainty associated with that measurement. This is still an open research issue. That's why we have published our dataset, and we are currently opening our testbed to encourage and allow our colleagues to research that topic and to test their own algorithm. I thank you for your attention. If you want to contact us, you can reach us at the LocURa4Iot@irit.fr email address.